So the next speaker for today is Finn Tegan. Finn, welcome.
Hello.
I can hear you, I can see you, so you
Perfect.
can share your screen.
It's in progress. So can you see my screen?
Yes, I can see your slides.
Perfect. Okay. Should I
So
start?
the next I'll introduce you. So the next presentation is by Finn Tegan, whose work is on Haskell inverted, automatic function inversion in Haskell, co-authored with Kai Oliver Prott and Niels Bockenberg. Go ahead, Finn.
Yeah, thank you. Welcome to our talk about Haskell inverted. I am Finn, like introduced, and I'm happy to present the work done by me and my colleagues who are also here today. And as you can see, some advertising, there's an artifact available which I'm going to refer in just a moment. So there is something to try out if you want to. So what is this talk about? Let us start by decomposing the subtitle, Automatic Function Inversion in Haskell. Well, let's start with function inversion. What is function inversion about? Let's say we have a function f that yields the output y for some input x. Then the inverse should yield set x for y as an input. And it's somewhat informal, but inverses in general have many applications. Some of them I list here. For example, parser printer can be seen as inverses. There has been work done before, compressor, decompressor as well, and serializer, deserializers also. In general, any form of encoder and decoder can be seen as a pair of function and inverse function, or vice versa. But there are also other applications. For example, there is work about the synthesis of parallel divide and conquer algorithms. If you have a language which has inverses available, you can indeed synthesize algorithms that can be computed in parallel. And one of our contributions is the implementation of so-called functional patterns, which will I come to in a moment. So what about the part in Haskell? Some of you may notice that the informal introduction to function inversion has a little flaw. It's only applicable for injective functions. But if we consider a language like Haskell, and we do not want to restrict ourselves to injective functions, well, we have to face the fact in Haskell that many functions are not injective. And one example, our favorite function here is the append function, which takes two lists and yields the concatenated list. And if we evaluate the expression empty list appended to the singleton list with 1, we get the list with 1, and we can swap the arguments and get the same result. So in conclusion, there is no unique inverse because there are, like here, two different values that lead to the same result, and that means that the inverse is not unique, and an inverse function in the mathematical sense does not exist. However, we can work around this problem by allowing multiple results for the inverse function, and that leads to the kind of inverse functions we are going to look at. And this is something like this, where we take the result type of a function as the input type for the inverse function and yield a list in this case, so multiple values of the arguments as a tuple, in this case a pair. That's the kind of inverse function we take a look at here, and that is the kind of inverse function we want to synthesize in the end. So last part in the subtitle was automatic function inversion in Haskell. That's quickly explained. That's the artifact I mentioned before. There's a Glasgow Haskell, so GHC plugin available. as an artifact and also at GitHub. That does all the things that I will try to describe here in the talk and that are also explained in the paper, of course, in more detail. All the things there explained will be done automatically by the plugin. So if you want to use inverses in Haskell, you do not have to do much. Just load the plugin and add a pragma at the beginning of your module, and you're ready to go. Okay, so what are the contributions of our work? Basically, we designed a framework for function inversion that enables the inverse computation of Haskell functions in Haskell itself. Support includes inverses and also partial inverses, which I won't cover in this talk. But you can basically imagine that you fix some of the arguments of the function to instead of returning all function arguments of the original function as the result of an inverse function. Most notably, our function inversion framework supports or limitedly supports higher order functions and also primitive types. And in conclusion, we really support the full Haskell 2010 standard. So everything you can imagine to write in Haskell can actually be inverted with our plugin. So it's not just restricted to some sort of model language or some subset of Haskell. You can invert any function you can write in standard Haskell. Moreover, other contributions are the implementation of functional patterns. That's a pattern matching extension that is known from functional logic programming, for example, in the language Curry. Basically, you can think of it as the extension of pattern matching by allowing function symbols in patterns and therefore allowing arbitrarily deep pattern matching in data structures. If there's time, I can show an example later on. But we have found a way to implement said functional patterns using inverse functions and also make this pattern matching extension available in Haskell for the first time. And like said before, there is a GHC plugin to do all the stuff automatically. So how is inverse computation achieved in our framework? The basic idea comes from logic programming. If you consider Prolog, for example, where we also have an append predicate available, we can call the append predicate with 3 variables as an argument, and the third argument of the predicate here is the result of the function. And if we call the predicate this way, we get the bindings for the 3 variable arguments, and in this case, the list of 1 can be obtained in 2 ways, like seen before, and Prolog does all the computation for us. And also inspired, we of course do not the same as Prolog, but we want to do something similar. So we want to extend Haskell in a way to enable logic computations. So we result in a functional logic extension of Haskell, and we require 3 variables and non-determinism. So that's the overall idea. How do we achieve the functional logic extension of Haskell? Basically, it all starts with a monadic lifting. And let us consider the following minimal example program where we have defined the list data type and the append function. And the first step in our monadic lifting is to do a pattern match compilation. It's well known, at least I hope. And all that we do here is to make the pattern matching, which we have here in the pattern positions of the function, explicit by moving it to the right side of the function and expresses as case expressions. And this is some kind of preliminary step for the actual monadic transformation that then takes place, which transforms the data type by adding a monadic type parameter to every component of a data type, and especially the pattern matching, which we have made explicit in this version, becomes a call to the bind operation of the monad we use for the lifting, which is M in this case. The rest remains mostly unchanged. This is some way simplified, because in the real monadic lifting we use for our inversion framework, we also have to lift the function arrow, which makes the code much more complex and less good looking. So I omitted it in this version here, but the idea remains the same. So pattern matching of the original function results in bind operations in the monadically lifted function. Keep that in mind. So if we have a monadic lifting, question is what monad to use for the monadic lifting, and this is sorry, I forgot to mention that of course in the final program we achieve after this transformation, we keep both the original definition and the lifted definition, because of course the user wants to keep a way to use the original definitions in his program. So we don't want to strip it of the original function he intended to program. So what's the actual monad we use for the lifting? It's quite complex, so I won't show the whole monad here, but I will try to give an idea. Like said before, we need support for non-determinism and free variables, and we further need support for both the implicit instantiation of free variables during the execution of the bind operation. We will see in a moment why. And at the same time, we require the ability to be able to do pattern matching on free variables, because we want to efficiently compute bindings for those free variables. And the solution we came up with is the use of two monads, which are nested or built on top of each other. And the first and inner monad is a simple non-determinism monad, which has the support for an explicit representation of free variables, and support for Haskell's call by need evaluation by representing the state of the computation in a heap. So the heap contains the binding of the free variables. And on top of that, we built the function logic monad, which is the one we actually use for the lifting, which adds the support for the implicit instantiation of free variables. How is inverse computation now finally achieved? It's quite, the idea is quite simple. The first part is that we compute the lifted function with free variable as arguments, and in the process, the pattern matching of the original function will result in the instantiation of the free variables we provided as arguments to the lifted function. And on the outside, we match the result of the lifted function, which we called with the free variables, with the input of the inverse function. So you can say that the matching process here in the second step drives forward the inverse computation and also maintains the laziness of the original Haskell function, in the sense that only the parts that are demanded are actually being evaluated by our inverse computation. So that is different from the naive approach, where you generate all possible input values and test if the result value matches with the input of the inverse function. So we try to be as efficient as possible with this approach. And in the end, the bindings of the free variables on the heap represent the result of the inverse function. Of course, that's only the overall picture. There is a detailed explanation in the paper. But to give you an idea how this works, let us take a look at an example. If we consider the initial example where we want to compute the inverse of append with a singleton list containing the 1, which would be this expression, we can now translate it into something like this, where we have some kind of match function. And well, this argument to the inverse function gets translated in the lifted representation. There's a boilerplate code that does all this stuff that I show here. And of course, the plugin does all the generation of the boilerplate code for you. So again, no work for the user of inverse function here. So the argument of the inverse function gets translated into the lifted representation and passed to the match function as an argument. And like said before, the lifted function of the one we want to invert is called with 3 variables as arguments. For the purpose of this presentation, 3 variables are represented as these small boxes. In reality, of course, they have a representation in the function logic monad, but since I haven't shown any definitions of the function logic monad, I figured that it would be easier to just use these small boxes. So what does happen now? The evaluation of match triggers the evaluation of this monadic function call in the second position here. And if we remember that the append function does pattern matching on the first argument, and this first argument is a free variable, and we also recall that pattern matching in the original function leads to the instantiation of free variables, we can conclude that this free variable titled A gets instantiated to the empty list and also non-deterministically to a non-empty list, which again has 3 variables as argument. So we instantiate it lazily. And some of you may recognize this is very, very similar to the process of narrowing from logic or function logic programming. And indeed, it is some form of narrowing. So let us follow the first computation branch here. If we instantiate the first parameter with the empty list, the result of the append call is just the second argument of the append call. So this reduces to a match call with the same list and the result of this function call if we instantiate A with the empty list. So after one computation step, we have to match the same list with the free variable B, and the matching is done very simply here. We can just enter the binding for the variable B and enter it on the heap. And afterwards, the matching was successful. So we now have one solution for our inverse computation. We remember that the inverse computation's result is represented by the bindings of the 3 variables on the heap, and A is bound to the empty list. Of course, we have to convert it back to the Haskell representation instead of our lifted representation. Also something that the plugin does for you. And B is bound to the singleton list. So we have the one solution where the first list is the empty one and the second the non-empty one. So let us follow the second computation branch here. Here, the result of the append function in the second case is the non-empty list, which has C as a first element, and the append call with D and B as the tail. And we still want to match the initial list with this expression. And now the match call triggers the evaluation. First, we can actually match something here. We can match the 1 with the C, because the 1 is the first element here. So we can enter C maps to 1 in the heap, and then can reduce the matching to the call that we have to match the empty rest list of this singleton list with the rest list of this second argument here, which is D appended to B. And yeah, now that's nearly the same as the first call we had here. again, the first argument is free variable, so we can non-deterministically instantiate it with the empty list and the non-empty list. In case of the empty list, we can return B as a result, which has to be matched with the empty list, and that results in the matching where we can bind the variable B to the empty list and have a successful solution here, successful computation branch. And again, the solution is represented by the bindings on the heap. A is bound to C const D, and C is 1, D is the empty list. So this is the expected second solution, where the first argument is the singleton list and the second argument is the empty list. And for the third computation branch here, we get this match call where we can quickly see that we have a mismatch because we want to match the empty list with a non-empty list. So this computation branch fails, and we have our two solutions in the end. That's basically the idea of our function inversion. Although presented quite simply, it requires, like I said, a lot of boilerplate code, which is automatically generated by our plugin. So what do we find in the paper? Of course, there's the function inversion framework explained in detail, the design of our monad, the type classes and type families involved in our framework are explained and defined there, and also some design choices discussed. There are extensions to the framework to cover higher order functions and primitive types. The latter are efficiently implemented using constraint solving. So we use an external solver to efficiently generate constraints and solve them during the computation with free variables if primitive types are involved. We provide an implementation of functional patterns, which also enable nonlinear pattern matching in an elegant way in Haskell. And last but not least, we also discuss partial inverses, which usually are used to make non-injective functions injective, but in our setting have some nice use cases where there are also non-injective partial inverses, which can be very useful in practice. So have a look in our paper. And of course, we also discover some related work, as always. So we compare ourselves to other approaches. For example, there are not many approaches that cover higher order functions or primitive types at all. Yeah, that would be all from my side. Thank you for your attention, and I'm happy to answer any questions you have.
Okay, thank you. There's a question by Jeremy, so I'm going to show it on the stage and invite Jeremy to the stage to pose his own question.
Hello.
Hi.
Hello.
This was fun. But so my question is not really about your main point. So if I put the function inversion aside, you have this monad FL, which, if I understand right, gives you logic variables as in addition to the non-determinism that we sometimes simple-mindedly think of the essence of doing logic programming in Haskell. And I wonder how useful that FL monad is for doing the other fancy logic programming stuff.
Right now, it's solely used for the function inversion purpose, but you could easily define your own DSL using that monad to support logic programming in Haskell. And although not tested, I am pretty confident that the Queen's program should be implemented or can be implemented using the FL monad.
So, of course, the Queen's program can be implemented without the FL monad. All you need is lists.
Yeah, that's true, but efficiently implemented.
Right. So Fruver's program is, he says, an order of magnitude faster than the one from O'Keefe's prologue book, because it uses logic variables to do comparison tests. I think that's the essence of what's going on.
Yeah, I will give it a try. I can come back to you, but
Yeah.
it should work.
Yeah. Okay. Well, I look for. I mean, if you don't, I will. So I'm quite interested in this. So great. Thank you.
Welcome.
All right. I'm kindly removing you from the stage, Jeremy. Marcus has answered, and there's a new question by Rudy Matilla. I'm going to show on stage, and I'm going to invite him over.
Hi. Hi,
Go
Finn.
ahead,
How are you doing? Yeah, so this is more of a comment than a question, and just something to bring up discussion, because I mean it's a plugin for GHC, which kind of limits how easy you could use it, because I mean, you have to build GHC with a plugin and a specific version. But I was wondering if you could do this using template Haskell. Say, for example, write the function inside a th quote, then apply a similar technique to produce both the original quoted code and an inverted version, like normal and invert, and then you pass the quote, and you get both versions, and of course use the technique that you described. Have that crossed your mind? Have you thought about that?
It actually did, and
Cool.
it would work in some sense, but there are some limitations to the template Haskell implementation. For example, you can't add exports, as far as I know. You can't add exports to your module. So if you generate an inverse function and you have an export list, it's actually not available in any other module than a module you use template Haskell in. So the decision to use a plugin was mostly because of practical reasons, and indeed we use some template Haskell within the plugin to exactly what you said.
Cool. Thanks for the answer.
Okay. I'm kindly removing you again from the stage. And Marcus has answered. So there's a new question by Jean-Philippe that I'm going to show on the stage. So questions are coming in quickly now. I'm going to invite Jean-Philippe.
Hello.
Yes, we can hear you.
Yeah, so there was another implementation, perhaps following up on Jeremy's remark, already 2001 of logic variables, and I checked in the paper quickly, and it seems you say it's too strict. Can you elaborate why?
Well, basically, we want to reuse the laziness of the function we want to invert, and this requires the deep embedding in the data components. And as far as I am aware of, this is not the case with the approach you mentioned. So we want to support non-strict non-determinism and non-strict logical variables in the components of data types, and that's not the case with that approach, as far as I remember it now.
Okay.
All right. Does that satisfy you, Jean-Philippe?
Well, I think it's not saying anything more than in the paper, but what I imagine is that when you evaluate, if you use, I think this 2001 approach is based on a state monad, and that could mean that it becomes too strict. But I think you also have a state monad in the background, don't you?
We use state and a state transformer in the background. That's right. But I will gladly come back to you. But in the short version, I would imagine that the embedding, as they use the library to embed Prolog in Haskell, and they also match the semantics of Prolog, as far as I know. And Prolog is definitely more strict than the inverse computation we want to have. It's like comparing Prolog to Curry, if you know it, which is a lazy functional logic language. And although not covered by the append example, because that's basically like an SLD tree, what I showed you, but there are cases where the demand-driven approach of our inversion is definitely more efficient than the generate approach that Prolog does. And that's the same reason why the embedding of Prolog of the work you mentioned is too strict for our purposes, because it builds the Prolog semantics or imitates the Prolog semantics.
Okay, thank you.
Okay, then I'll remove you from the stage and mark your question as answered. So there's another question, this time from Gergo Erdi. I'm going to show it on stage and then read it out because he doesn't have a mic. So he says, is the transformation done on the service language or on core?
It's not on core. It's done in this some kind of on the surface language. So we do a Haskell transformation, but we check that the core code is correct afterwards to ensure that our transformation is right. But the transformation is done on a surface language level.
Okay, thanks. I'm gonna mark that as answered, and then there's I think a final question for this session by Katsutaka. Who I'm going to invite to the stage.
Okay, so
Katsutaka.
what? Hi.
Hello.
So can you hear me? Okay, why do you use the FM monad instead of using Fisher and others monad for writing non-deterministic computation in Haskell? So I think that it is quite powerful to emulate many computation carry, in my understanding.
Yeah, the main difference is that the library by Fisher and L does not have an explicit representation of free variables, which is crucial for the matching algorithm we use. However, we thought of combining both approaches because the library by Fisher et al. Incorporates true call by need, so it incorporates true sharing, and indeed we already started on working combining both approaches, and the main reason we haven't done this in the first place is because it complicates much of the code. So it requires, for example, the use of more language extensions. The boilerplate code gets even more complex, but in theory and also in practice, as far as we know for now, because it's already working, we could do so to gain an even more elaborate combination of the monad defined by Fisher and the one we use. But we require the explicit representation of free variables, which is not present in the approach by Fisher et al.
So I think in the Fisher's library we can emulate the free logic variable by using the non-deterministic generation and the sharing operator in the library. So
semantically, that's equivalent. That's right. But the problem with that is that you have to run the generator in order to match afterwards. And if you have an explicit representation of free variables, you can actually insert the binding on the heap, which is far more efficient than generating all possible constructors and then fail for every one except for one.
Thank you.
Okay. Thank you. I'll kindly remove you from the stage, Katsutaka, and mark your question as answered. So yeah, this brings us to the end of the first session. Thank you again, Finn.
Thank you
for giving the presentation and answering our questions. It is now a break time until 3 o'clock. So I'll be pressing the take a break. It seems that everybody will be kicked out of the session then, but at 3 o'clock or slightly before 3 o'clock, we will resume with the invited talk by Mathieu Buspluk from Tweak about linear Haskell and its practical applications. See you then.